The way in which we get data off of the data logger is using some software to read it. So the data logger unscrews, there's an optical sensor inside, you connect that inside the data logger and then hook it up to your USB port and then turn the software on or launch the software, and then it hopefully will recognize the device. It's taken me a little bit to get this thing to recognize, but in the lower right the interface is connected here, and then in the lower left it shows me goes down and senses the pressure and temperature of the water. And so what I can do is I can launch the device, and it takes a little bit to do that, and then it basically shows you the serial number, how good the battery is, which is nice. We still have a battery. This thing is a lithium-ion battery that lasts for several years, and then you have to service it by sending it into the company. You can have it sense pressure, sense temperature, and so on and so forth. But for the most part, what's important for us is we need to determine the logging interval. Now, many times these data loggers are used to log long-term water level changes. And I'm going to set it up for that after I do the slug test so that we can gather some information about our long-term water levels in this well for the rest of the semester. But for today, what I want to do is be able to sense the water level during our slug test. So we're going to put in this bar that's called a slug, which I showed you in the previous video. The data logger will already be down in the well underneath the water level far enough so that when I drop the slug in, it's not going to knock it off or jab into it or something. But I want to have a logging interval that is quick enough to capture the changes, but not too quick that it fills up the device's data storage capacity. That's kind of the trick here. And so in other years we went to Sunnyside Elementary, and I may be giving you those data, but Sunnyside Elementary has a very, very sandy aquifer, and it only takes about 3 or 4 minutes for the entire recovery to take place. The one on campus that I'm going to show you takes much longer. For the bail down test, the one well took something like 34 minutes and it wasn't completely recovered. The other well took over an hour and it was still had 12% of the recovery left. So these are not quite as coarse, not quite as highly conductive sands. So maybe I don't need a 1 second. I could make it 10 seconds or something. But I think I'll set this for a delayed start and start putting all the material down in the well, do the experiment, and then end it at some point. So I could take my computer out in the field, but this is my interface right now for classes and for job interviews for the water science professor next week. I don't want to risk taking my only laptop in the field right now. And so I'm just going to take the data logger out there and hope that 11 a.m. is good. So at this point, my 1 second interval should be good. It's going to start at 11 a.m. The computer should know my time. It's 11:29 a.m. And so I'm going to press that delayed start. The logger is now set up for a delayed start, and I'm going to assume that it's going to work. So at this point, I can close HoboWare, and the next video is going to show you, after I do the experiment, it's going to show you how to download those data so that you can see what the data look like and how to manipulate them and export them. Today we're going to do a slug test, and the first thing we need to do before we put anything into the well or pull any water out of the well is you have to measure the static water level. We did this last time. Let's see what it did in the meantime in about a week. So I've got my water level meter. It works. Always test your batteries. So this is monitoring well 2, the deeper one. .34 feet. I don't remember what it was last time, but I think it was pretty close to that. So that's where we're at, 11.34 feet. Now what we want to do is get prepared to lower the slug into the well. So this is a slug. All it is a solid plastic bar. It's denser
than water, so when it goes in it doesn't float or anything like that. It's attached to a rope. I will give you the dimensions of the length and the diameter so you can calculate the radius, do the pi r squared times h to calculate the volume. That volume is equivalent to an amount of water that we put into the well. And if you know the interior diameter of this well, then what we can do is calculate how much water was put in as an effective slug of water. So it's the same kind of idea. All right, before I do this, I need to know exactly where to put this slug. So what I want to do is get it ready so that it's right above the water table, and then when I'm ready to start my experiment with the data logger, it's going to go down below the water table. I'm going to leave it sit there, tie it up here for a while, and then wait for whatever response to dissipate. We can gather enough data, and then we'll pull the slug out after it's equilibrated. So I'm not sure how this is going to work. I've never done a slug test on this well before. I anticipate that it will probably take 20 minutes or so to equilibrate. But the first thing we need to do before we can do anything like that is we need to tape our water level indicator or some other kind of measuring device to the end of the slug so that I know exactly how far the slug is lowered. I know that it's 11.34 feet to water, so I want to have that at 11.2 feet or something hanging above the water before I do my test. If I put it in the water before I start my test, I'm going to get a funny reading. And so how we usually do this is just tape it on with some electrical tape, and it usually works pretty fine. It doesn't have to be pretty, it just has to be solid. You want to make sure that it's on here tight enough that the water level indicator doesn't get any bending or scraping or anything like that. We want to make sure we tape the end of the line here in a couple of places. The exact depth and location on here isn't important. I just need to know that I'm close to the water table and that when I drop it in, I'm fully submerged into the rope section. That's all that really matters. The exact position of the water level and the exact position of the data sonde aren't that important. I know what the water level is in the static sense, and whatever the pressure is, we can calculate that stuff later. So there's no real way to calibrate it right now. I'm going to put another couple pieces of tape on here. That's probably good enough. All I need to do is make sure that this thing doesn't get messed up while it's being lowered into the well. You can stop. Okay, so here's our data logger. All it is a pressure transducer and temperature meter. There's a long-term lithium-ion battery in here, so this thing lasts for very, very long periods of time, like 5 or 6 years at least, before you send it back to the factory to have the battery replaced. And I've tied it onto a thin but sturdy nylon rope, and what I want to do is lower this down into the well at a place that's low enough that it will always be below the water table. And I don't know exactly where that is. I could be monitoring this with my water level indicator. It's not really that important. What I will do in this case is I know that this is a 42-foot deep well, and I can feel where it's going to hit the bottom. I'll let it touch the bottom, and then I'll bring it up a couple feet just so it's hanging off the bottom. That's going to be well below any area where the slug is being lowered. So the top of casing is here. The top of the static water level is 11.34 feet, or whatever I said before. The bottom of this well is 45 feet below top of casing, or about 42 feet or so below ground surface. So there's plenty of distance between where this data logger is going to be hanging in the well and where my slug is going to be moving in and out. And if I have a nice smooth rope like this, there shouldn't be any way that it's going to be hung up on that. And everything should be good. This is heavy enough. So I don't have it fully connected to this string, so I'm going to be extra careful while lowering this into the well here. I already pre-measured out at least 40 feet of rope in my driveway, so I kind of know where I'm going. Now there's a little bit of displacement that will take place when I lower this data logger into the well, but a pretty small amount. So I'm going to be able to wait 5 minutes or something. By the time I get this all tied up and get everything ready to go, that should have dissipated. Ideally, I would take another water level indicator and make sure that that has happened. But in this case, I'm showing you the demonstration, and I'm going to probably give you some other data. Oh, I already feel it. It's hit the bottom. So that's 45 feet or so. So I can pull that up a few feet. And now what I can do is tie this thing on here. It doesn't matter exactly what the depth is that it's tied on, because I know the static water level. So that to me is going to be an adequate process. Okay. Here's what it looks like with the data logger tied onto the string into the well. You can see I've tied it onto some sort of an eyelet here. That's the lock where the cap would have a lock go through. But there's plenty of space inside the well here for that slug to fit in a 2-inch PVC monitoring well. So this should be an acceptable setup for us to do our slug test. All right, so here's our slug. Our water level indicator's on here. It's sort of a way we can measure the depth. Because there's a couple inches of distance here between the bottom of the slug and where the water would be located when it beeps, let's say that's 2 inches. So I'm going to be around 11 feet. That's where I want to have this thing hanging before it goes in the well. I've waited a sufficient length of time that the water level has probably recovered to its original value. So now I want to carefully, very carefully lower this into the well. Feet, 11 feet. So 11 feet is right there. That should still be above the water table. When I take the data and put it on the data logger, if I see a little bit of a strange uptick before I actually got this thing in, then I know I've made a mistake here. Then I need to know how far to put this in. And one of the things I forgot to do is measure the length of the slug, but it was about this far, so I'm going to lower it into here. And here's how we do it. We want to do it as quickly as possible, but not so quickly that you lose control. Ready, set, go. And I could hear it slop into the water. So now what I'm going to do is I'm going to hold that there and try to tie this up so that it doesn't move at all inside the well. I need a pen or scissors or something. I think this will probably work okay there. That's fine. Same thing with this part here. Let me get some tape. Squirrel method. Now, I don't know how long it's going to take for this to recover, but I can wait 10 or 15 minutes or so. So in the meantime, I'm going to go over to the other well. We're going to do a bail down test, and I'll show you how to use the conductivity meter and the pH meter to measure some aspects of water quality. This part of the exercise is going to be taking a bailer. This is a different kind of bailer. It's a plastic bailer. Normally these are things that are considered disposables. So you would leave this one inside the well if you had a contaminated well or something like that. But we don't have contaminated wells. We just need some kind of bailer that we can repeatedly use. These are something around the order of $15 or something like that. They're pretty cheap. So there's our ball for the ball valve. There's the hole. So I'm going to get some water out of this well. So let's get an idea of, ooh, it smells very irony today. Let's get an idea of what some of the water quality parameters might be for a well like this. I've got a conductivity meter that senses temperature pretty accurately, And I've also got a pH meter. And there are lots of other things you can do. There are some multi-parameter sondes. Some do dissolved oxygen. Some will do things like nitrate and a whole variety of other types of in-field experiments that can be done. But it's really typical to do conductivity, temperature, and pH. So we can do that. My spacing's too narrow. Okay, so that's good. And all we have to do, pour this into our, pour this into our bucket. You can tell it's a little bit cloudy in here. And I can put in my probe for the conductivity and temperature and the pH. So the first part here is really just to get everything wetted a little bit, let it come to some kind of an equilibrium. The temperature of the water is 9.8 Celsius. It's rising here in the sunlight and with the air contact here, but it's 9.9 now. It'll be 10 in the short there. It's 10 already. So usually what I do is get this thing wetted, let everything kind of come to something close to a stabilization, and then I do one more bale, put it in there so that you're getting something that's like a fresh temperature and fresh conductivity value. It's a little bit more accurate that way. This conductivity is not too salty. It's 863 microsiemens with non-flashing. And with flashing, which is an actual temperature corrected conductivity, it's 1214 microsiemens per centimeter. So there are two different ways you can read this. One corrects for temperature, one does not, and I'll let you know what those are like when we do the conductivity. I'll probably give you some for 3 wells at Sunnyside Elementary. But this is basically how this procedure is done. So let's see how much of a change there is between this water that's been sitting here for a little bit. pH is 7.99, and it actually looks pretty stable. It isn't changing very much here. 7.97. It's pretty stable. So let's try another baler full. See if we can get maybe a more precise amount or a precise reading here. That seems empty. No, not too empty. Okay. Okay, this should be a little bit better. 9.2. 9.1. So 9.1 Celsius is the temperature. 1208 is the specific conductance with its flashing degrees Celsius on this meter here. That's the temperature corrected one. And if I change the mode, it's 845 microsiemens without the degree Celsius symbol flashing. That's conductivity, which has conductivity varies with temperature. The other one is temperature corrected. Okay, for pH, I'm at 7.80. 7.80. So that's the best way to do this. This is not the best pH meter. It's a field handheld one, and it's kind of wild. It goes all over the place, but you get the idea. Let's stop the video here, and we can go back and check on our slug test. Okay, so it's been about 15 minutes. Like I said, I'm not sure exactly how long we need to wait, but this might be long enough. Clean that up later. Get a good grip on this thing. So now I'm going to pull, the slug is in there. Now what I'm going to do is do a slug out. So now what happened is, this is equivalent to a bale down test. I've taken a certain amount of water out. I shouldn't have jiggled it first, so we'll do our best with that. But I think we can get a good set of data from this slug out. Now we let this thing wait, and we're going to see the opposite response on the data logger's profile, and I'll show that to you in the next video. Okay, so here's our data logger, This was down pretty close to the bottom of the well for both the slug in and the slug out part of it. I forgot and jiggled the depth meter a little bit on the way out or after I did the slug out. But we'll see what the data look like. Now I take this and connect it to the computer and we'll be able to figure out what the pressure was like in the well and temperature. We're at monitoring well 2 right now, and I thought I would just do another bailing test just so we can compare pH and conductivity with the first well with monitoring well 1. So I'm going to take a couple bailers out just so we can get something a little bit more representative down in the aquifer. This is the kind you can really hear hit the water table. So let's get a good video of that next time I put the bailer in. Why don't you come up here, Betsy? Ready? Put it right up close. Okay. Let's see what we get here. .1 degrees Celsius, and it's rising real quick. I'm going to do one more bailer just to get a fresh amount. Let that thing come to some sort of equilibration. So 8.6 Celsius, I was able to get more out of it. The more you get out of it, the more, you know, this steel and the PVC isn't warming that water a little bit. So 8.6 Celsius, 760 microsiemens for conductivity, and 1103 microsiemens for specific conductance. So this one's a little bit less salty than the other one, but they're broadly about the same, within 10% of each other. Okay, that's a good place to, oh wait, this pH here is 8.06. Okay.
Okay, I'm back home. I have my data logger, and what I'm going to do is unscrew the top of this, if I can do it with one hand. Nope, I guess I can't. Hold on. Okay, so this data logger is an optical system, or the reader portion is an optical system. So right here, this is the place where the optical sensor is. And in this device, this is the reader portion of it. So what I'm going to do is put that inside of here. Not sure how to do this, sorry guys. Here, let me hold it up like this. What we can do now is take this data logger, hook it up to the computer, which I've done, and we can go to the point where we stop the device. Want to stop the logger. The logger has been stopped. So now what I can do is whoop, I don't want to do that. Perform a readout of the logger. So I've got to figure out how to do that. Readout device. So now it's downloading the data. it's asking me where I want to save this. So I'm going to do UWGB well for, what's the date today? 11/2020. So I'm going to call this well number 2. And in this case, we're going to get data that are in degrees Celsius, PSI, and so on and so forth. And we can make those corrections after the fact. So if I press plot, what this will do is it'll show me the results. So here what we have is a couple of things. The blue line shows the temperature, I believe. So here's the temperature up at the surface. That's in degrees Fahrenheit, so it showed that it was about 68 to 70 degrees Fahrenheit. Some of that could have been because I was holding the device in my hand and it was a little bit warm. And then as soon as we put it in the water, it got cold. And this is when we took it out of the water. So it never quite thermally equilibrated to the water, but it was getting close. And the temperature of the water in Fahrenheit was down here near 50 degrees. If I were to change this to standard international units, then I could get a different result, but it looks like it's recorded in PSI and degrees Fahrenheit, so we're going to have to deal with those. Okay, the black line shows the pressure, and that's the left-hand graph here, the PSI. So it goes from 14.5, which is about what atmospheric pressure is, and then as soon as I put it underneath the water, it shot up here. It probably went up a little bit higher of pressure because I went all the way to the bottom of the well. Then I started tying it off, and once I tied it off, it was pretty much at an equal state. It might have been changing a little bit because the temperature was still equilibrating, and that pressure is a calculation based upon temperature. But for what we're dealing with, we're going to be looking at data that start right before this spike and end right about here. So these two spikes, these saw teeth, those are our slug in and slug out tests. So think about this. Right at this moment, I put the data logger in here. It's recording. It's a static pressure. Then I put that slug in. What would the slug do? The slug would displace a volume of the water. It would push the water level up in the well, and therefore the pressure where that pressure transducer was would increase because you have an extra maybe couple feet of a water column. So that pressure difference can be calculated and determine how much of a footage difference that is. So we can see really what our equivalent drawdown, slug in, slug out displacement are. Then this nice decay curve here, this is the decay curve that represents the water level going back down to its previous value. The really good thing is that this particular slug test, it only took a few minutes. So here we have 11:40 and there's noon. And so probably 3 or 4 minutes is all this slug test took to do, which is about on par with the one out at Sunnyside. So this is kind of similar. I waited a little bit of time. We did some other stuff like monitoring well one's conductivity and temperature and pH and stuff. And then I came back. Then I pulled the slug out. So that is effectively like bailing out a volume of water. So the pressure went down. Remember, the pressure transducer is staying at the same place in the well. What's happening is that the column of water above that is either rising or falling. In this case, it fell dramatically when I pulled the slug out, and then it came back to some equilibrated value. There's one little tick mark there. That we're going to have to correct because I screwed up and I pulled on the string a little bit. Anyway, not a big deal. Accidents like that happen, and you sometimes have to modify the data and correct for things that happen if you bump something. The alternative was, now that I know this, I could go back and I could do a slug test on this well or a well nearby, and it might only take me 5 minutes to do it once I have everything set up because the recovery's quickly. So then we waited an extra period of time, about 15 minutes or so, and then I took the pressure transducer out of the well, and so the pressure dropped all the way when it came back to atmospheric. And the only difference here is that I was holding on to this, so maybe there's a little bit of a grip there or something. But look what happened to temperature. I took it out of the well, and the temperature immediately warmed up in my hand. I was holding this in my hand, and it got all the way up to 72, and that's basically what the temperature is in my house right now. So things got kind of warm, but the pressure stayed at atmospheric. So we don't need the data here. We don't need these data. All we need are these two areas of data right there and right here. So I'm going to save these and export these into Excel. Let me see if I can figure out how to do that quickly. Export table data. We want all of these things. We can export it and worry about what it is later. And I can save it as a comma separated value, and that we can import into Excel. So let's confirm that that actually happened. Oh, there it is. It's right there. All right, so here's our data. If I open this in Excel, it'll take a little while. But we're going to basically be able to get the data for this particular data set from when I set it up in my bedroom at my office here to when I drove to school, did the experiments, and it automatically turned on at 11:30. That was my predetermined turn on time. I had to change it after the first video. And then it was recording the entire time until I got it back home. So the data look like this whenever this thing loads. First launch of the day is always a little bit slow. So here's the date, the time, and if I go a little bit farther, I'll be able to get the time shows up as seconds. Do you see right here in the toolbar 11:30? That's 11 hours, 30 minutes AM, but 1 second, 2 seconds, 3 seconds, 4 seconds. So this data logger was set to record data every 1 second. Okay, so now that I have this, I'm going to stop this recording, start a new one with the data put into Excel and modified a little bit. Now that we have our data downloaded from the data logger into a comma separated values spreadsheet, we can start manipulating it so that we can calculate our K values from our slug test. So the first thing you want to do is open the data in Excel and then save it as an actual Excel file. So let's do that first. I'm going to make sure that I change this just a bit so that it's clear. Change this to Excel workbook. Put it on my desktop with millions of other files. Okay. So now I've got an Excel file with a bunch of information here. On the left in column A, I have the numerical list of data values. Column B is the time, right? So we actually have the time in seconds because the data logger was set up to record every second. Column C shows absolute pressure in pounds per square inch. We're going to do this one in feet because your previous lab for monitoring well 2 was dealing with feet, so I thought I would stick with this. Temperature in degrees Fahrenheit, we can leave that there, we don't really need it. The rest of this stuff we can delete, so we can kind of ignore that stuff. Okay, well, what do I really want? I don't really need the rest of this stuff either. Okay, what I really want to have at this point is I want to convert my absolute pressure into sort of an H0 minus H value. It's still in pounds per square inch, and then we can convert that onward. So let's call this H0 minus H PSI. And what that means, it's going to be a value that's 0 for these early values, and it's going to be something longer later on, or something higher later on. But before we do that, we have to realize that I've got literally thousands and thousands and thousands of data points here. Let's see, how many data points do I have? Oh, I went past it just a little bit. Come on, come back. I have about 3,880 lines of data. Why? Because I have 2 slug tests separated by the time it took me to start my data logger at home, go to the well, get everything situated, do the slug tests, wait a bunch of extra time, and then come back. So what I want to do is search through the data and actually find out when the valuable data are, and then just get rid of all the other stuff. So I'm going to do that real quickly here, and then I will start a new video. Okay, we're looking at the data that came out of the data logger, and I've cleaned it up a little bit. I've deleted some of the extraneous columns past D, and what we have is a record number from 1 to about 8,500, a date and time to the nearest second, an absolute pressure, in this case in PSI recorded by the pressure transducer. You can set the units to kilopascals if you'd like. It doesn't really matter. We have to convert it to feet or meters of water column anyway. And then in this case, a temperature in degrees Fahrenheit. So what we need to do first is determine, out of these 8,500 data points, what is useful. Well, so the first thing you want to do is plot columns B and C against each other. And when I do that, this is what I find. Let me zoom in just a little bit here. And so the bottom column, or the bottom row here, this is the pressure transducer recording essentially atmospheric pressure before it was lowered into the water column. So then we lowered it in the air portion of the well. When it hit the water level, it started increasing its pressure as it went beneath the water until it hit the bottom of the well. Then I pulled it up just a little bit, and then I tied it off. And once I tied it off and everything stabilized, what we're looking at here is a stable, even value. And after that, the data points shoot upward. This is me lowering the slug into the water. And then they decay exponentially downward. And then I waited for some length of time. I fiddled around a little bit with the ropes. Then I pulled the slug out, lowering the pressure that the pressure transducer was recording. And then as the water level in the well came back up, it reached a new equilibrium. And then after some point in time, I pulled the data logger out of the well, and then it was recording atmospheric pressure again after that. And this is the point where I got home and turned it off. Okay, so what I need is this slug out and this slug in. And the way you want to figure that out is just mouse over the top of the data points and see about when that is. So right around here at 1141 until, I don't know, maybe 1145. This is our usable data set. And over here, somewhere around 1159, over to maybe 1203, 1204, something like that. Okay, so now we can go back to the data, scroll down until we find 1141. 1138, 1139, oh, there's 1141. So now what we want to do is take a look at these data. Watch the pressure. There's going to be a little bit of change here and there as things are going in and out of the well, just in the air pressure changing things a little. If the wind blows, it might push the air column or the water column down a little bit, depending on how windy it is. Those little fluctuations aren't so important. What's really important is when you see a big change. So everything is 27.86, 0.88, 0.878. Things are pretty stable until right here. Then there's a big jump. And so this record of 4 data points, I think, is our good stable marker. So what we're going to do here is we're going to put H minus, equals, no, H minus H0. It's just our title. But it's, sorry about my Adobe updater thing. We're going to be doing this in PSI. So this is what we have. Oh, it went back to the original one. Sorry about that. Oh, we might as well fill this up again and put this in seconds. We're going to make a column for H minus H sub 0 in feet. And then after that, we're going to have a different column. But we can worry about that column later. So let's go back down to these data for 1141. I think it went too far. Okay, so here's where we're at. let's fill in H minus H0. So here we'd put equal, and the actual H is here, minus, and let's use 27.878 for our H0, our static depth to water. It's measured in pressure, but that's okay. And it doesn't measure that we're measuring it with a pressure transducer that's buried under the water. All we're looking for is an absolute change in the water level. It doesn't matter if the numbers are positive or negative. It really doesn't matter. You plot them up and you get a nice curve. So what we want to do here is we want to fill down for the data set that we're dealing with, which goes until about 11:45. So we can modify this a little bit, see what we get. Things look like they have stabilized pretty well. Let's see if we can go a little bit farther. Maybe there's some more decay. No, not very much here. So I'm going to leave that one alone. This record over here starts here. We have steady water level, steady water level, steady water level, a very small blip, not worth worrying about. And then look at the jump. The PSI increases by 0.63 PSI. That's pretty significant. And then it goes up here to 0.94. So we don't have to worry about this row 694 because the slug was partially in the water when the data point was collected. What we want is the maximum recorded water level. That's really going to give us our H sub 0. It's going to give our maximum displacement. So this is the cell that's going to be most important here. Let's highlight that one. Whoops, I made a mistake. Not that one. This one. So this is our initial, and this is going to be times 0. And after this, each one of these, we can do the previous one plus 1, because we know every data point is 1 second apart, and then we can fill down for this entire record. Oops. Keep going here. Oops, I screwed that up. Let's go back here. What am I doing? Fill down. So if I'm looking at my cheat sheet here, our initial value is 0 seconds, right? And then our value here, we have to calculate H equals our H minus H0 in feet. So what we want to do is use our PSI here and do that. So I'll do that in the next video. What I've done now is I've highlighted all of the data that represent the point in time from the start of the data logging to right before the slug test. We don't need those. So to make it easier to manipulate the data, we can just delete those rows. What this does is it brings us all the way up to sort of our 11:41 start time, where we have some static water levels. I could probably delete this one too. Then we have the data that we care about right at the top. And I'll do the rest. I won't show it, but I'll do the rest. I'll clean that stuff up so that you get an idea of what I'm looking at here. Now what we want is, we know what the difference in PSI was during the slug test. We want to translate that into water. Now I did tell you that you could calculate how much water equivalent was put in by looking at the length of the slug and the diameter of the slug. And you may need that type of information at some point, depending on how you reduce the data. But we can do it a different way. The first thing we can do is, we're recording the water levels. We don't really need to know how much was taken out or how much was put in. What we can do is we can translate this. Now the conversion factor I've put up here at the top, 1 PSI equals 2.31 feet of water. So if I have this value in PSI, then I can basically multiply that value by 2.31 to get the amount of feet that this really is. So let's start up here, equals this value times 2.31. And if we fill down, you'll see that the water level rose by about 2.17 feet. Now if you think about that, let's determine whether that's a reasonable value. Our slug was probably a good 4 feet tall, but it didn't completely fill the well. So maybe half of the volume of that well was filled by the bar and the other half was still surrounded by water. So that's reasonable. It's not a few tenths of a foot, but it's also not 20 feet. So our calculation is in the ballpark of what we would expect a reasonable value to be. So let's continue filling that down until we get to 1145, where we had ended before. Okay. So at this point, it's 0.007623. Now think about that. That's the same as 0.01 feet. That's less than what we're even able to measure with our electric meter. So we really don't care about a lot of these data. We probably don't need all of these, but it's okay. We're just going to get some data at the end. We're probably not going to want to plot and determine things like slope using all of these. We'll use the reasonable data that plot on a straight line. So that's what we need at this point. We have enough data. I don't know why these are taking a little bit of time to show up here. Okay, we have enough data that we can go ahead and make a graph. That's what I'll show you in the next step. The last step, so we can examine our data, is to plot our head ratio, h divided by h0, versus time. That's the plot that we would need on page 195 of Fetter, figure 5.22. So this straight line plot, which is plotted on semi-log paper, shows us what our T37 value is. We need that T37 value, or where that head ratio falls to 37% of the initial value, so that we can calculate our K value and determine a hydraulic conductivity. So first thing we do is make another column here, h divided by h0. That's our head ratio. So this is a column we really care a lot about, and we're going to plot that with respect to time here. So the first thing we want is we want to highlight cells that we're going to use in a different color, just to make it easy. So I'm going to choose orange here. Everything before this tells us something about our static water level. We've converted our difference in head, which was measured as PSI, to our difference in head, which is measured in feet. And this basically tells us our initial value. So with the other method where you're doing the bail down test, we had to go and calculate that value. We had to project backward. With a pressure transducer, we don't need to do that step. We can look and determine exactly what this is. Now, is it going to be perfectly accurate? Maybe not. We're recording data only every 1 second. We could probably record data more quickly than that, whatever the pressure transducer can handle, but this works pretty well. So what we need to do is make this calculation. It equals our head value divided by, let's use that value. That's going to be our H0, our original displacement, 2.172093. So I'm going to use that. Our first initial value has 100% of the displacement, or that ratio is 1. Now if I fill down with this, I can calculate what that ratio is. We're down at less than 1% down here at the bottom, so we really don't need to worry about these data. If you look at Fetter's book there, that head ratio gets down only to 0.1. So we don't even need to plot that far down. We might only need to plot the first couple of minutes. Probably first 2 minutes or so, maybe 3 minutes at the very most. Here we're at 5–6%, something like that, of the original. So it doesn't really matter what you choose. Let's go to about, I don't know, let's try all of them. Let's see what it looks like when we try all of the data that we looked at before. We can plot this value h over h0 versus time, and when we do that, we can see what we get. So if I go up to Insert, Chart, XY Scatter, they're going to be on the wrong axis probably. Well, actually, they weren't. So what we have here, I'm going to put on a new chart, or on a new sheet here. Move chart, new chart. So this is going to be slug in. So our initial value right there, that's the full value, and it really rapidly decayed after that. So what I want to do is turn this into a logarithmic plot. And so I can go over here to the format axis problem, or a pane, and change logarithmic scale. And this is really interesting. This shows us a nice straight line graph, and then the data get kind of strange over here. What it's showing you is the limitation of the pressure transducer's ability to measure the pressure. And so these are the steps, sort of the precision of the data here. And because they get farther apart, that's because this is a logarithmic scale. We don't really care about these data down here in the lower right anyway. And we certainly wouldn't want to do a best fit line with those kinds of data. We would want to choose something only that's up here. And so since we're going to, this is only 10% of the original value, that's what Fetter shows his cutoff in figure 5.22. So basically, maybe we can look at cutting it off around 100 seconds. So if we go back here and we right click and we select data, and instead of 256 data points, oops, let's just do 100 data points and see what we get. That's much better. Much nicer straight line graph. Little bit of something funky here. I'm not sure what that is. That could be me trying to tie it off and tape it down, and I might have jiggled it a little bit. But those data are going to work themselves out. If this is more of a significant impact, you could delete these particular rows. There's nothing wrong with deleting bad data if you have reason to do that. But let's just leave it in here for now. At this point, we can add a trend line. And this trend line doesn't really look right. It's linear. But we have an exponential function here because we had to plot it on a logarithmic axis to be able to get a straight line. So we actually want to choose exponential. And when we do that, we get a straight line solution. Some of the data at the bottom are on one side, in the middle they're on the other, and then the other at the top they're kind of on the other side. This isn't a bad solution here. We can display the equation, and we can display the r squared value. Let's make this a little bit larger so we can see it. When we do that, whoops. When we do that, what we see is I'm having troubles here, guys. So what we see is a really beautiful r squared value. This is a nice straight line set of data. And we have a really easy to deal with equation like we did last time. So if we want to find out a particular value, last time we set this to be x equals 0, and we could tell the original y value, but in this case we can use this very equation to go and calculate our T37. We already have the original, now we can use this to our advantage. So at this point I'm going to stop there and let you guys watch the next video where I reduce the data and show you some other useful hints. Our next step is to treat the data for the slug out, our second slug test. Normally you measure values for the slug in, and then you wait until it equilibrates, and then you pull the slug out. And sometimes people do this a couple of times, and you can take average values if one of them is kind of very different than the others, and or you make a mistake during this process, then you can throw away the data. But in this case, let's see what the data look like. I know I pulled on the rope in a way I shouldn't have, so we may have to remove a few of those data, and I'll show you how to do that. So I looked around and I saw that 27.9012 was a common value for the absolute pressure before our 11:59 time range. So I'm going to use that as my initial value here for h minus h0. There are a couple of data points in here where things are pretty close to 0, but I was fiddling around untaping the rope and getting ready to pull the slug out. So I'm going to consider these to be static water as well. Then there's this value, which is a big jump. It goes to 0.733. So that's fairly significant. I'm going to call this transitional, though, because it's not the maximum amount of displacement. That's the 0.8192 psi. But before I can do that, and I'm going to label that as time 0, that's my highest point. That's the instantaneous highest or lowest value, the farthest away from the static water level. In this case, it's a drop in pressure because I pulled the slug out, which would be the same as pulling a certain amount of water out, about 2 feet of water. So what I need to do is calculate this in feet. So I can take my value in psi, multiply it by my conversion factor, which is 2.31 feet of water for every psi. And that means that I had an equivalent fall in 1.89 feet of water in that column. So that's pretty useful. Then I have to make my time go up equals 1 plus the line before it, so that when I fill down here, I'm going to be able to make this calculation for the whole data set. Whoops, let's go back up here. So here's what we've got. We've got our time after about 60 seconds. It's dropped from 1.8 something feet down to 0.8 feet, but that's still a lot of displacement left from the original value. That means we need to keep filling down until we have a value that's much lower. I think I had written down by looking at the record that it was 1204. Yeah, so let's see what this looks like if I go to here. Now we're in the ballpark of something very small, less than 0.01 feet. That's what's showing. Here it's down to 0.005, 0.01. So probably something to this point here. This is probably the only thing that's relevant. All right, well the last step is to do our h over h0 again. So this is going to be our normalized head drop. And when we do that, equals h, our difference here, divided by negative 1.892352. So this value, our normalized head, should always start at 1. Their instantaneous value at time 0 should be the maximum displacement. That means 1 or 100% of that displacement existed then. So we can fill this down and see what we get. Let's go all the way down to see what this looks like. There we are. So we're way less than 1% here. This value basically says that it's down to 0. So where do we make the cutoff? Not quite sure, but we could take a look at this by plotting it. So let's plot it. Let's see what we get. Let's go all the way up here. Oh, went too far. We want that, and we want our time. So I'm going to select that column as well. Oops. And it went too far. It's a little tricky here on a touchpad on this laptop. Okay, so now we can go back up to insert. We're going to insert a chart, and we always want to use scatter plot for most scientific things at least. And here's what we have. Let me move this chart to its own value, and we're going to call this one Slug Out Monitoring Well 2. Okay. That's pretty good. Look at those 2 data points. That's when I accidentally started pulling out the data recorder out of the well and I went, put it back in right away. It really didn't mess up the rest of the trend, but I don't want those 2 data points in there. Those 2 data points are going to mess up a little bit a best fit line. So beautiful decay curve here though. This is exactly what you want to see other than those 2 points. And so the first step we want to do is let's make this, double click here. There we go. That's what I want. So let's make this a logarithmic scale again. So what is it telling me? Any negative or zero values cannot be plotted. This is a good result to get. So what it means is I can't plot anything that's zero or negative on a logarithmic scale, because you can't take the log of zero or a log of a negative number. What that means is I need to truncate my data a little bit earlier so that I don't intercept anything that has a zero value. And that's okay, but it's just not going to plot that. So now we have something that's a little bit different. This is probably because it's a slug out. It looks a little bit stranger, but we have that same artifact where these things are spaced farther apart, the limitation of the pressure transducer's ability to measure pressure. And we don't want this. We want to use something that's more of a straight line. Now this one plots a little bit longer length of time. Last time we used 100 seconds and we cut it off there. I think that's still reasonable. We can use 100 rows. So let's try this again. Select data. But in this case, we can't make this value go from 542 to 100. We want it to be 100 above this. So let's go to 366. Try this one again. And let's see what it looks like. Not bad, except these two data points, we know they're erroneous. I know they're erroneous because I pulled on the string. So it's okay to delete those data. Let's go in and find out what they are. This is 28. I don't know why it keeps doing that. 28 and 29. So I just want to get rid of those. That's at 28 and 29 seconds. To do that, I go here, find my 28 and 29, and just delete those rows. What did I do? I kind of messed something up. I messed up the seconds here. So I'm going to need to fill this back down. I know that I deleted 28 and I deleted 29. So I'm going to make this one 30. And then everything works well again. So I've just deleted 28 and 29. Now when I go back to my slug out value, those two data points disappeared. Doesn't matter that I have a gap there. I'm going to get a pretty nice best fit line. So let's try that. Let's add the trend line. We can choose our exponential fit again. We can display the equation and the r-squared value. And we can make it a pretty nice size so we can actually see it here. All right, 0.9995, that's a really good straight line data set. And we have an equation that we can do something with. So what do we want to do? Remember, for the figure in Fetter's plot on page 195, figure 5.22, we've got a straight line. We want to know what T37 is. Well, it's kind of hard to get that off of this graph accurately because we have 0.1 and we have 1 on the side, and I could probably add in some extra tick marks here and change some things on the axis. I could make the minimum values, let's see, minimum units. Anyway, I'm not going to mess with that right now. I don't want to waste time on the video. What we need to do is find out what is the x value time for our y value that's 0.37 or 37% of that initial displacement. So what we're going to do is we're going to make y equal 0.37. We divide both sides by 0.9862, and then we take the natural log of both sides. So we're going to have the natural log of 0.37 divided by 0.9862 equals negative 0.014x. The reason is when you take the natural log of e, you only get what the e to the x, whatever the exponent was on e. It kind of gets rid of the e function. So it's a really handy thing to do, and then when we do that, we can calculate what our T37 is by another simple division of the 0.014. That's the point at which I think I'm going to leave this, and I'm going to let you guys calculate the K value for both the slug in and slug out for monitoring well 2, and then compare that to the data you got for last week's lab from that same monitoring well using the bail down test and the Vorslev method and Bauer-Rice bail down test methods. So this is a pretty interesting way of saying, let's see what we get when we use a very different kind of method on the exact same well. Okay. What I've done here is cleaned up things a little bit. I made the graphs a little bit nicer with the appropriate X and Y axis labels and a title, and I made the fonts kind of the right size and put tick marks in and things like that. What I've done here on this last page where it says final calculations, I guess the last page is the screenshot from the data recorder, but the page here, or the tab that says final calculations, I've put the date of the field measurement, the Saturday the 11th of April, today, and I have basically put in the slug in best fit line, the slug out best fit line here, and what we've been able to do is what I've been able to do is actually give you the values. So I showed you how to do this. This equation right here in row 7 is the equation of the best fit line off of the graph. This is basically Fetter's 5.22. And I've kind of shown you the steps to go through calculating T37, which is the same as solving for X. And so we can also see where 0.1, 0.2, 0.3, 0.4, so 0.37 is over here. That's about 47 seconds or 42 seconds, and that looks right. It actually took me a while. I was getting some kind of error I was making on the bottom one, and I was getting 7 seconds. But it turns out it's 70.4 seconds. It's a little bit different, but all of these pieces of information are highlighted here are the ones you need. So what you can do is take this equation for calculating K using the Vorslev method, plug in the T37 for each of these two cases, plug in the L sub E, which is 7 feet, the radius of the well, and the radius of the well screen plus the sand pack. They're all given to you above, and you can calculate K. What I'd like you to do is calculate the K for slug in and for slug out, compare the two, maybe determine an average, and then compare these values with what you calculated last week using the bail down method for both of those wells, especially compare monitoring well 2, the same data. I'm going to leave that here and send you the rest of the data for Sunnyside the following week. I think this will be enough for this particular week. Bye.